Hello everyone. So today we are going to study FIR filter. So first we will use FIR filter in Python, and then we will use the same input to the Python which we have given for FIR filter for filtering and filter coefficient in Vivado, which is our Verilog language. Okay. So we will implement in Python as well as in Verilog. That's our goal. So with the goal being clear, let's get started. So here's a fairly simple FIR filter Python program. So what we are going to give to the Python is this input here. You see this few lines of code between 20 to 24 line. There is a x low variable which will hold an array of sine wave which will have a frequency component 5 Hz, and there will be one more variable, array variable, which will hold the sine wave with frequency 500 Hz. Okay. By the way, this NP is numpy, and it is imported as following here. Line number 7 and few more imports have been done for filtering and all. These are Python libraries. Okay. So you have made this two variable xlow and xi, which will hold the low frequency component 5 Hz component and 500 megahertz component, 500 Hz component, and you will add them together. We know if you add two signal, it will have both component, both sine tone. Now, why we are doing this x plus 5 and scaling it and rounding it? We are doing this because we want to export it into Verilog or Vivado tool, which is a Xilinx tool. And what we want to do, we don't want to have a negative number there, and also we don't want to have any decimal fractional number like 2.3495 like that. So we are scaling and rounding it, as well as we are uplifting it, like raising its level from negative to a positive side. As we know, if you just clamp a signal or raise its DC component, it will not affect any frequency component in it. As well as if you scale it, it will just be expanded in y-axis domain, but it will not change any frequency component of it. So it's fairly equal or fairly equivalent to add a DC component to it and also round it by scaling by some factor. This will be our input. Now let's talk about our FIR filter. So this line number 13 and 15 here will decide our FIR filter. So what we are going to do, we are going to design a FIR filter using a FIR windowing method, as you can see here, and it will have 21 taps. Taps means its impulse response will have 21 terms. Okay, and what are these two extra parameters which are in our square braces? This parameters tells you that between 0.0 and 0.1 times of your Nyquist frequency, that is fs by 2, sampling frequency by 2, your gain of filter will be 1, and consecutively between 1.0 so gain will decrease from 1.0 to 0 after that linearly. Okay, that's what this line means. So it will be a constant gain up to some multiple of frequency, Nyquist frequency, and then it will be decreasing linearly from gain 1 to 0 up to Nyquist frequency. And now we are scaling this taps because we want to use it in the FPGA for the same reason I explained before. You don't want any negative components and don't want any But yeah, we can have a negative component here, but we don't want to have any fractional component. That's why we are scaling, but not adding a DC component to it. Because adding a DC component will change the characteristic of taps, but that doesn't change the characteristics of signal frequencies. So with that thing, let's get started and run this program. So if you see, the red color one is your unfiltered signal, which has both the frequency component, a high and low component. So if you see this variation here, the variations here, the small variations here are the high frequency component. But if you zoom out and look at the higher picture, if you see, there are 5 cycles, 5 sine wave cycles in this complete picture, because we have taken 0 to 1 second duration. By the way, this line number 18, time is taken as following: np.arrange will give you equally spaced values from 0 to 1 with a spacing of 1 by fs, and fs here is 1024. So it will give you 0 to 1, that is 0 to 1 time, and with a spacing of 1 by fs, or sampling period. So here if you see, there is a 5, after filtering there is a sine wave, and there's such 5 sine waves here. So that is 5 hertz. It's repeating 5 cycles in 1 second. This complete axis is 1024 sample that correspond to 1 second. So you have 5 different cycles. That's why it is a 5 hertz component. So after filtering, we got 5 hertz component, and we can also verify it using FFT, which I have done below. You can see in the red color plot, you have both component, the low component and the high component in frequency. The 5 hertz component here, and this is your 500 hertz component. But when you see in the filtered one, you have 5 hertz component, but you have a very less. Filtering cannot completely eliminate 100% of your other signal, but it eliminates to a good extent the 500 hertz component. So this shows that it is filtered now, and all we have to do is to take this tap scale components coefficients into a file and use it into Vivado, as well as we will use this input X scale to give into the Vivado FIR filter. So let's start Vivado. Complete FIR. Okay, so now we are in Vivado. In Vivado, there is certain flow which I will tell you later, but we have 2 files, like a FIR filter.v file, which you have to instantiate. Okay, and there are some instantiations here which you can do, and map your FIR filters variable to a IP which Xilinx provide you for doing all the computation for FIR filter. Except you have to just give the input, that is coefficients, and your input coefficient as well as input signal in terms of binary. You can give in decimal also, but binary is preferred. Now if you go into simulation sources here, you'll find FIR TV test bench. In the FIR test bench, what I have done here is I will read some samples. I'll read some samples from this file, demo file text, put into a memory, local variable, and on the top of it, I'll get the output from the FIR filter. What output will give using that input. So this is just essentially same file which we have created in the Python here. Here, demo file text. Now you have to do one more thing. We have to instantiate IP IP called FIR filter, FIR compiler, and in that FIR compiler we have to give our coefficients. So these were the coefficient which we got from the Python. Okay. So in Python, if you see variables, this tab scales as this variable -12, -1, -36, which is the same thing here. So when we go in Vivado again, and we'll just copy and paste here with the comma separation. Okay. And now we have to give the number of coefficient, which is 21. Sorry, 1. Number of coefficient set is 1 only. So we have to put this coefficient vector here. Number of coefficient set is 1 only, and number of coefficient is 21. And then we go for channel specification, which will choose as basic, and we'll select the frequency for specification. Input sampling frequency, which will be around 1024, so I'm using 0.001. Clock frequency is arbitrary here. Okay, and implementation will use coefficient width. We have used 16-bit coefficient plus 1 for sign, so that's why 17. And data which we have put into that text file, data demo file, right, that will be 16-bit because we have stored it in Python as 16-bit here, you see. So now with that we press OK, and it will customize IP and it will generate it. Now it's generated. Now we need to run the simulation to see. We have already given input, we have given the coefficient, we have instantiated the FIR filter. We have to see the behavior now in the test bench. It takes some time, hardly a minute or so. Now we have to expand this and run this simulation here. And as we are running it, you see you are getting a sine wave. So this is the output. And next is there is some AXI protocols which will be part of FIR filter. So input is this thing here and output is this here. So if you see, now I should stop this simulation and show you the output and input. You see on here in the input, if you zoom in, you see in high component there is a low component sine wave is there, which you can see like with the shape of this, right? And when you zoom in, there is a high component thing which is changing like this here, like a rapid change is high component, and the bigger envelope is like a low pass or a low signal. That because that is what we have created in the Python. Now, if you see the output is a fairly low component with a slight high component thing, but which is negligible. As you can see, it's a clean sine wave But as we saw, there would not be possible to 100% eliminate the high component. That's why a small component of high frequency is present, but overall it is a low pass signal with a 5 Hz of frequency. This is how we have started from Python, ended up in the Vivado Verilog, and filtered a signal. Now, if you run the synthesis and run implementation generate bit stream here, you'll be able to put into FPGA and filter any signal with this Vivado IP. So that's how we go from simulation to Vivado, then Vivado simulations, and then to actual board. So that was it. Thank you all.